Welcome to the deep dive. You know the drill by now. We take your research, all these fascinating, dense sources, and we just cut right to the heart of it.
Get to what you really need to know.
Exactly. And today we are strapping in for what feels like the ultimate mental journey. We're diving into quantum physics, the realm where, everything we think we know about reality just takes a sharp left turn.
It really is the ultimate intellectual challenge. I mean, we're leaving the world we know, the classical physics world where things follow nice, predictable laws.
Where a ball is a ball and it stays where you put it.
Precisely. And we're going down to the subatomic level. And down there, it's all about probability, uncertainty.
Yeah.
It's a whole new set of rules.
So our mission today is pretty straightforward. We're going to try and pull out the core ideas and, what they actually mean for the real world.
Yeah.
We want to give you that shortcut to understanding why this micro world is just so fundamentally strange, but also why that strangeness is, well, it's powering our future.
And to start, I think we have to frame it right. Quantum physics is just the science that helps us understand tiny things, electrons, photons, that kind of stuff.
Okay.
But the key thing to get right from the start is that the rules are completely different. This isn't Newton. It's not even Einstein, really. Here, just looking at something,
Just observing it.
it changes the experiment.
Yeah.
It's not a passive act anymore. It's part of the whole system.
It's funny, if you ask a classical physicist where something is, they can, point to it. It's right there.
Right.
But if you ask a quantum physicist, what do? They give you this incredibly complicated math equation.
Exactly. And the three concepts that really govern all this deep weirdness are probability, this inherent uncertainty that Heisenberg codified, and maybe the most important one, superposition.
Superposition. Okay, let's unpack that. Because this is the one that really forces you to just, suspend all common sense.
It does.
How do we even explain the idea that a particle, like an electron, isn't in one state, but it's in all of its possible states at the same time?
The best way is to think about it mathematically first. So before you measure anything, this particle is described by something called a wave function.
A wave function.
And it's not a physical wave like in the ocean. It's a mathematical description of all the potential places or energy levels the particle could be in.
So it's a list of possibilities.
A list of all possibilities held at once. Your sources have that perfect example. An electron at a certain energy level is literally here and elsewhere at the same time.
Wow. So it's not that we just don't know where it is.
No, that's the key.
It's that it genuinely doesn't have a single definite position yet.
That is the absolute core distinction. It's holding all those possibilities open until, that is, something forces its hand.
And that brings us to the real drama of quantum mechanics, the measurement problem.
Okay, so the particle exists as this cloud of probabilities, this superposition. What happens when we actually try to look at it? Because in my world, the macro world, me looking at my coffee cup doesn't change a thing. Right. But in the quantum world, the act of measuring it, of looking at it, forces that wave function to collapse. All those infinite possibilities just instantly resolve into one single definite outcome.
Right.
You go from this state of maybe to a single is.
So the very act of trying to pin it down, to define its reality, fundamentally changes its reality.
It does.
That sounds less like physics and more like some cosmic game of hide and seek.
It is precisely why the famous thought experiment, Schrodinger's cat, was created, to show just how bizarre, how counterintuitive this idea of collapse really is.
Right, the poor cat.
The poor cat.
Trapped in this hypothetical box, its life depending on a radioactive atom that has a 50-50 chance of decaying.
Exactly. So before you open that box, the quantum trigger is in superposition. It has both decayed and not decayed.
So the cat is too.
Therefore, the cat, which is linked to it, is also in superposition. It is simultaneously both dead and alive. The system is just undefined. Until you look.
But I have to ask, where is the boundary then? I mean, we don't see this in our lives. My coffee cup is definitely on my desk.
All right.
It's not also floating in the kitchen.
And that boundary is a concept called decoherence. It's basically the quantum system constantly interacting with its environment, with heat, with air molecules.
So the outside world is constantly measuring it.
In a sense, yes. All these tiny constant interactions force a big object, like a coffee cup, to collapse into one single state so fast that we never see the superposition.
Okay.
The cat experiment is so powerful because it highlights this deep paradox. Physics doesn't really have a clean, clear line dividing the weird micro world from our certain macro world.
That really helps frame the complexity. Okay, so if looking at one particle changes it, what happens when two particles are linked? Fundamentally connected no matter how far apart they are?
Now you're getting into entanglement.
Entanglement.
This is where things get even stranger, if you can believe it. It's when two or more particles are linked in such a way that they share the same fate.
They share a state.
Their properties, like spin, for example, are perfectly correlated. And the amazing part is, it doesn't matter how far apart you pull them.
So wait, if I measure the spin of particle A over here, I instantly know the spin of particle B, even if it's on the other side of the galaxy.
Instantly. The state of one immediately influences the other. The distance is completely irrelevant.
That's what bothered Einstein so much.
It really did. He famously called it
spooky action at a distance.
Spooky action at a distance. He just couldn't accept it.
Because it seems to break one of the most fundamental rules of the universe, right? Nothing can travel faster than the speed of light. But this correlation, it seems to be instantaneous. How do physicists today deal with that?
That's a brilliant question, and it gets at a really common misunderstanding.
Okay.
Because while the correlation is instantaneous, you actually can't use entanglement to send information faster than light.
You can't, but why not? If they're linked, why can't I just wiggle one to send a Morse code message to the other?
Because the outcome of your measurement is still fundamentally random. So you measure particle A, you get a random result, let's say spin up. You know instantly that particle B is spin down, but you couldn't control that. You got spin up. It was random.
So I can't encode a message into that randomness.
Exactly. You'd still need to call your friend on a regular phone, a classical channel, and say, hey, I got up, so they could make sense of their down result.
So it shares information, but it doesn't allow for communication.
That is the vital nuance. It keeps relativity intact, but still shows this incredibly profound, non-local connection. It's what makes entanglement not just a weird idea, but the engine for so much new technology.
Okay, let's pivot there. Let's go from the theory, from the superposition and the spooky action, to the actual tech, because the sources are very clear. This isn't just theory anymore. It's driving a real revolution. We have to start with quantum computing.
Yes. Quantum computing is basically taking superposition and entanglement and putting them to work. It completely changes how we process information.
So our normal computers use bits, right? A 0 or a 1. Simple. How does a quantum computer get around that?
It uses qubits. And because of superposition, a qubit isn't just a 0 or a 1. It could be a 0, a 1, or kind of a blend of both at the same time.
An infinite range of possibilities between 0 and 1.
And then you use entanglement to link these qubits together. And that's where the real power comes from. If you have, say, 50 normal bits, you can have 2 to the power of 50 states. But a quantum computer with 50 entangled qubits can explore all of those states at the same time.
That's just a staggering amount of parallel processing. So they're not just a little bit faster. They can solve problems that are basically impossible for even our biggest supercomputers.
Exactly. And the sources point to a few key areas. The first is complex simulation.
Like for science.
Yeah, simulating how molecules interact, designing new drugs, new materials for solar panels. A quantum computer can model these things perfectly because it operates on the same quantum rules.
And then there's the big one everyone talks about, encryption.
Encryption. They are a massive threat to the way we currently secure everything online. There are algorithms that could, in theory, break modern codes exponentially faster than any classical machine.
But they can also be used for good, right? Like in optimization problems.
Oh, absolutely. Things like finding the most efficient delivery routes for a massive fleet of trucks, or modeling financial markets, or even making AI algorithms smarter. Anywhere you have a huge number of possible solutions, a quantum computer can search through them all at once to find the best one.
It really does sound like magic, but there has to be a catch. I mean, why don't we all have one on our desks?
The catch is a word we used before. Decoherence. Maintaining that superposition.
They're fragile.
Incredibly fragile. Qubits are so sensitive. The tiniest disturbance, a vibration, a stray magnetic field, a temperature change, and poof, the wave function collapses and your calculation is ruined.
So you have to keep them incredibly isolated.
Which is why they look like those giant, complicated chandeliers. They have to be kept in these special chambers, cooled down to just fractions of a degree above absolute zero. It's a massive engineering challenge.
That puts it all in perspective. But it's not just about computers. You mentioned quantum physics is also changing how we understand energy and matter itself.
It is. I mean, the more we learn about how electrons behave inside materials, the more we can start designing things from the ground up.
So instead of just mixing things together and hoping for the best,
we're designing materials atom by atom. We can create things like high-temperature superconductors or super-efficient solar cells by deliberately arranging atoms to create specific quantum effects.
We're engineering with the quantum rules, not just discovering them.
That's the breakthrough. And it goes into medicine, too. Modeling how proteins fold, designing drugs that target very specific cells. It's all based on these principles.
And we can't forget about communication, using these weird quantum rules to make our information more secure.
This is where quantum cryptography comes in. Specifically something called quantum key distribution, or QKD.
Okay.
You use single photons to send parts of an encryption key. And if a spy, an eavesdropper, tries to intercept that photon to read the key...
And the measurement problem kicks in.
Exactly. The very act of them looking at it collapses the photon state. It leaves a footprint.
An undeniable trace, so the users know instantly that someone was listening in.
Precisely. You turn the fragility of the quantum world into a feature, an unhackable security system. And that's why these experiments with quantum light are so foundational for the future of secure networks and laser technology.
This has been a huge dive. I mean, we started with the absolute weirdness of superposition, saw how just looking at something changes it, and then saw how entanglement links it all together into these incredible new technologies. For me, the biggest takeaway is that the reality we actually live in is just so much more complex, so much more fluid than what our senses tell us.
It is a profound shift in how we see the world. I mean, the quantum universe forces you to accept that uncertainty isn't a flaw in our measurement. It's a fundamental part of existence. Nature, at its core, seems to run on probabilities, not certainties.
And that's a powerful lesson in itself, just for how we approach knowledge.
It really is. The quantum world is always pushing us to ask more questions, to test things, to discover. It's not a finished book of rules. It's this ever-expanding mystery.
Right. As your sources said, every experiment means a new surprise, a new door to knowledge.
Exactly.
So here's our final thought for you to chew on. Quantum physics has completely overturned our most basic ideas about physical reality, things like location and certainty. So what other fundamental rules that you accept every day, maybe in non-physical things like economics or social behavior, might also turn out to be just as fluid, just as probabilistic when the next big discovery comes along? Something to think about.